This is Darrell presenting Apple's Develop in Swift Fundamentals for Xcode 13. It's Unit 2, Lesson 3 on structures. Structures are vitally important in Swift. Most data structures in Swift are structures. The alternative is classes. We're going to learn about structures first, and then classes, and then we're going to talk about the difference. A structure can have properties and store values. A structure can have methods that provide functionality. You can define initializers for structures to set up their initial state. You can extend structures. Structures can conform to protocols so they can provide standard functionality of a certain kind. We capitalize type names in structures using upper camel case, and that way all of our types are upper camel case and capitalized. The structure itself is defined with we start out with the struct keyword, and then we can put our functionality inside the braces. Inside, we use lower camel case for property names or inside the structure. Here we have a structure with one property. The structure name is upper camel case, which is normal, and property names are lower camel case, which are normal. We did not specify an initializer. However, by default, Swift creates a initializer. It's called a member-wise initializer, where it includes as parameters every property in the structure and lets us initialize one without creating an initializer itself. In this case, we call the initializer by using the name of the type, person, with an uppercase, and then the arguments, the first argument is name, and we pass it a string because name is of type string. That creates a person and creates an instance of the person, which we put in this person lower constants. This person here is lower camel case, and because identifiers are case sensitive, this is of course different from the type. And then we can access the members of the struct by just using the dot syntax. So we have person, we can print person.name, and it prints out Jasmine. Structures can have behavior. In this case, we've added a function to the structure, say hello, which prints out the message. When you have a function inside a structure, it's called a method. And so here we create a new person whose name is Jasmine, and then we can call the method by using the dot syntax, and then we use the standard function syntax where we have parentheses at the end. In this case, this method does not have any parameters, so we have just parentheses without any parameters inside. Here we've created two instances of a struct. Our struct is shirt. It has two properties. We use the default member-wise initializer to create two shirts. Note that the member-wise initializer, the parameter names are in the same order that the properties are defined in the struct. So size was first, and so size is our first parameter, and then color was second in the struct, so color is our second parameter. So we create two separate instances. One is a constant named myShirt, and one is a constant named yourShirt. Here we have a structure car with three properties, and we have four methods. We create two instances of car, first car and second car, and then we can call the methods on a particular instance of the car. So the first car is the one whose engine will start, and then the first car is the one that will drive. The second car, we have not called any methods on it yet. We've already been dealing with structures in this course. String, int, and bool, which are built-in data types in Swift, are all structures. And so here we have initializers, default initializers for string int, and bool, where we provide no parameters, and it creates instances of each of those structures with default values. In the case of string, it's an empty string. In the case of int, the default value is 0, and in the case of bool, the default value is false. Here are examples of just calling the initializers directly on the types. So we create a new string, we use parentheses, we put in the appropriate parameters. In this case, we have no parameters, so we get the default string. It's always useful whenever you're dealing with a new data type to look it up in the documentation. So on developer.apple.com, they have documentation for each of the built-in data types, and you can look up all of the different initializers for the string type, for example. And you can see that you can create an empty string by just using the string.init with no parameters. Or, for example, I could pass in a character and create a string from a character. And then there's a whole bunch of additional initializers for string. In this structure, we've set a default value of 0 for count. So we could create, by default, we could create a new odometer instance by specifying a count as a parameter, or by specifying no parameters, in which case the odometer will get the default value of 0. It is required that before initialization is complete, all properties have a value. In this case, all properties do have a value, because even though we didn't pass a parameter with the count property, it had the property count had a default value of 0. Even though our odometer has a default value of 0, it still gets its member-wise initializer with count as the parameter. So we can still create an odometer where we specify a count. So in that sense, you could say we have two initializers, one with count and one without count, where we get the default value of 0. Let's look at member-wise initializers in a little bit more detail. Here we have our person struct, which has one property, which is a string, and it would not make sense to have a default value for a name, so we do not have a default value. As a result, we get one member-wise initializer. We can create a person and we specify the name and we have our string, and that is the only way we can initialize this person struct as it's currently implemented. In this case, we have a bank account which has two properties: an account number, which is an integer and it does not have a default value, and a balance, which has a default value of 0, but you can alternatively specify a balance when you are creating the bank account. As a result, we have two member-wise initializers for this struct. The full member-wise initializer, we pass both parameters, and in the second member-wise initializer, we only pass the account number, which does not have the default value. And in that case, the transferred account, the balance would have the default value of 0. Here we have three structs, and we show use of their member-wise initializers. First, we have a shirt, which has two properties, and then we create the shirt where we specify the size and we specify the color. We have a car, which has three properties. None of them have default values, so we create a car and we specify our three properties. Remember that we always, for the member-wise initializer, we always have to specify our parameters for the initializer in the same order that the properties exist in the struct. So make comes first, year comes second, color comes third. And then here we have bird, where we have can fly with a default value of true, and then weight and color. So we have three properties. Because one of the properties has a default value, we have two member-wise initializers. In the first, we do not specify the can fly, and so we only pass two parameters. And in the second, we pass all three parameters, including the can fly. In both cases, the parameters that we provide are in the same order that they were defined in the structure. Here we have a temperature struct, which is one property, Celsius, and we create a temperature instance using the initializer where we pass in Celsius. But what if we wanted to create a temperature with Fahrenheit? In this case, we would have to manually calculate the Fahrenheit temperature and then use the Fahrenheit value when we create our, use the converted, we'd have to convert that to Celsius and then use the Celsius value when we're creating our second instance of temperature. And that is not desirable. Here we've modified our temperature struct to have custom initializers. We have our Celsius initializer where we pass in a Celsius value and then we set the Celsius property to the parameter that we passed in. Note the syntax here where we have a parameter which is labeled Celsius and we can access that by just Celsius. But we also have a property of the struct which is named Celsius. And we cannot access that just by using the name Celsius because we have two different values which are both referred to by Celsius. So we have to use self.celsius to access the struct property. But in any event, we pass in Celsius, we set the property based on it, and at that point, every property in our struct is initialized, so our initializer is valid. In this case, we only have one property, so setting every property is easy. But what we've also done here is we've created a second custom initializer where we pass in the temperature in Fahrenheit. And the only difference between the initializer, at least how you call it, is the label. The parameter is still a double in both cases. However, the compiler knows if we call temperature with the Fahrenheit as the label, it will use the Fahrenheit initializer. And if we call temperature with the Celsius label, it will use the Celsius initializer. In this case, we have a value Fahrenheit, we calculate Celsius, and we set the property Celsius to be that value. In this case, we did not need to use self because there was nothing. There was only one in this block. There's only one thing that Celsius can refer to, and that is the property of the struct. And then we can create two different temperatures, with one using the Celsius initializer and one using the Fahrenheit initializer. Now, one other interesting thing here is we had a member-wise initializer which used Celsius and set it. But as soon as we created our custom initializer, the member-wise initializer no longer existed. Swift provides the member-wise initializer for you by default on structs if you don't have any custom initializers. But as soon as you create a custom initializer, then it assumes that, hey, since you're creating custom initializers, we're going to get rid of the default initializer and you will have to re-implement it yourself if you really want it. If you are doing the playground labs that are included with the Apple curriculum, now is the time to open up the structures.playground and do the exercises for struct instances and default values, and then the app exercise workout tracing. The methods we've dealt with so far are instance methods. They're meant to be called on an instance. So here we have an area method which calculates the area using the width and height of a particular instance. So we create a instance of size, and then, and only then, we can execute the area method of the specific instance. Here we have a struct odometer. It has one property, count. It is an integer, and it has a default value of 0. We're going to need to increment the mileage, and we're going to need a method to reset the mileage. So here's our increment method where we have a function and we're modifying the value of the property. But in a struct, if you're modifying a property in the struct, then you have to mark the method as mutating. That's important because if we had a constant instance of the struct, then we would not be allowed to call the increment function because a constant struct cannot be modified. And so we have our increment where we increment the count. We have another increment where we can increment by a particular amount. And then, of course, we have our reset function, which sets the count back to 0. And all of these are mutating. In the next slide deck, we're going to learn about classes. And classes do not have this requirement. So when you're changing a class, you don't need to put mutating. Here we have a temperature struct, and what we want to do is we want to be able to get the temperature out of our struct in Celsius, Fahrenheit, or Kelvin. And here's a poor way to do it. In this case, what we're doing is we're creating 3 separate properties, and then whenever we create the temperature with our member-wise initializer, we have to initialize all 3 values. And we're relying on whoever is calling the initializer to correctly calculate these values. And you can see this would be very error prone. Your data in that you're trying to refer to one temperature, and you can just have internally inconsistent information. Here's an alternative implementation where we save 3 separate we still have 3 separate properties, and we have 3 separate initializers, and each initializer calculates all 3 properties and saves them. And this is an improvement over the prior one, because if we're going to, we're at least our struct is internally making sure that it doesn't make any errors, but it's still error prone because we still have 3 sources of truth for our temperature, and we're relying on our code to always update them successfully. Here is a better implementation where we have what's called a computed property. We have Celsius, which is a normal property, and we can initialize our temperature with Celsius. And then we have Fahrenheit, which is a computed property. It does not actually have any memory to store any information. Fahrenheit is of type double, and anytime we access the Fahrenheit computed property, then the structure will calculate the computed property based on the stored properties and the code. If you want, you can now perform the challenge to add support for Kelvin. So we have Celsius as our stored property, we have Fahrenheit as our computed property, and you should attempt to add Kelvin as another computed property. You can pause the video to do that. Here's the solution. We create Kelvin. Computed properties are always of type var. They are never of type let. Kelvin is of type double, and we perform the calculation. We don't need a return statement because there's only one line in this method. If the computed property had multiple lines, then we would need the return statement on the last line, or whichever line was actually returning our double. And then here you can see we initialized a temperature with Celsius of 0, and then we print out the current temperature .Kelvin to get the Kelvin temperature. Swift allows you to have property observers. Anytime a property is changed outside of an initializer, you can write your Swift code so that a particular set of code is executed. In this case, total steps is a variable. A property observer would make no sense if it was a constant. Total steps is of type int, and anytime it is set, just before it is set, this will set will be executed, and then it'll print out the new value, and you can access the new value with new value, NEW, then capital V ALUE, and then after total steps is updated, then the did set code will be executed, where when you do the did set, you can access the old value. So you can see the new value has already been set to total steps, and then the old value, whatever its value was, and that way you can print out how many steps changed. This, using property observers, is a great way to guarantee that no matter how your property is changed, a particular set of code will be executed. Here we are executing our property observer from the prior slide. We create a step counter. It is a variable. Again, property observers don't make much sense for constants. And then the default steps are 0. And then we modify total steps to be 40. And then we have, so that will trigger 2 property observers, the will set property observer, and then the did set property observer. And then we change the total steps to 100. And again, the will set property observer is executed. And then we update the total steps. And then the did set property observer is executed. Swift also supports type properties and methods, also known as static properties and methods. We use the static keyword. Here we have a temperature struct, and we have boiling point, which is a variable. However, because it's a static variable, it belongs to the entire structure, temperature structure, as opposed to any specific instance of the struct. So we can access temperature.boiling point without even instantiating any instance of our struct. And in this case, we're setting boiling point is a new constant, and we are setting it to be the static temperature.boiling point. Now, it helps that in Swift, our convention is to capitalize types and to have instances and properties being lower camel case. So that way, anytime you see something capitalized, in this case we see temperature is capitalized, just by reading this we can infer that temperature is probably a type, and so boiling point is a static property. We can also have static methods where the method belongs to the type as opposed to any instance of the type. And here we can have a static method which converts from Fahrenheit to Celsius. And we pass in the Fahrenheit value, we get the Celsius value out. We do not need to instantiate any instance of temperature. A struct is a value type. It is copied on assignment. So here we have a size struct. And then we create another size, which is a struct, which is a copy of the first one. So now we have 2 separate sets of memory, both of which have the width 250 and height 1000. Then on the first one, we set the width to be 500. And you can see on the first one, then we print out the widths on both of them. And you can see on the first one, the width is 500 because we changed it. But that did not change the value of the second struct. So anytime you assign a struct, you end up with 2 copies of the struct, each with their own memory. And modifying one will not modify the other. This is fundamentally different from classes, which we're going to learn in the next slide deck. Classes are reference types. So if you copy a class, the second class would be pointing to the same memory location as the first class. But with struct, when you copy a struct, it's a value type. So when you copy it, you have 2 sets of memory, each with their own values. Self refers to the instance itself. In this case, we have description, which is a computed property, and it looks up the value, the structure property color, and it does it by using self.color. It's not always required. In this case, we don't need self.color because when we look at when we use the identifier color, there's only one possible instance that it could be, the property for the structure itself, or the property for this particular instance of the structure. However, in this case, self is required because when we use the word Celsius, there's two possible values it could mean. It could mean the parameter we passed in or the structure property. The parameter we passed in has a more local scope. So Celsius without self would mean the property we passed in, which means that in order to access the structure property, we have to use self.Celsius. That concludes this slide deck. If you're following the Apple curriculum, you can complete the remaining exercises in the Structures Playground. And again, this slide deck is produced by Apple and is licensed by them under the Creative Commons Attribution Non-Commercial Share-alike International License.